Namaste. Good morning, guys. All right, today what I want to talk about is I want to talk about motion. All right, we're starting a new unit, and it's about how things move, and it's the study of how things move. And you're saying, like, why would you even study something like that? It's just so obvious that things move. All right, why is there even like a science around it? Well, the reality is because it's very important to human beings. As a human being, you're not a plant, okay? You have evolved to move around, and that's very important to us. And I want you to just do this thought experiment for a minute. If you think about someone who's disabled, let's say they're paralyzed from the neck down, and so they can't walk, they can't move their arms. That's a very tragic event when that happens. That's hard on that person. And now the reality is, I mean, do they need to move? No, not physically. I mean, someone will feed them, someone will take care of them, things like that. But you're taking a lot out of life if you as a human being can't move. And to the point where we in the modern age have invented things as much as possible so that people who have lost a lot of their ability to move can move again. Things like electric wheelchairs, things like prosthetic limbs for people who have lost legs, things like that. And we do this because it is so important for us as human beings to move from one place to another. One of the worst things that could happen to you would be if we were to lock you in a small room like a prison cell, and you're stuck there and you can't move around and you can't see things and whatever. And especially during this pandemic right now that we're having, what's one of the most important things that you can do for your mental health is to get up, walk around outside in a safe place where you can, obviously social distancing, but move around, feel the sunlight, feel the wind, do stuff like that. And historically, and I'm saying this because it's important that you learn why you're learning what you're learning. Historically, for human beings as animals, obviously we need to move because we hunt, because we grow plants, we do things like that in order to get our food. Again, we're not plants, we're animals, so we have to go get our food somewhere. And then as our race, our species grew, we started to move even more because different groups started to trade with each other, and that became important. And if you think of like the Stop and Shop in town, okay, all the stuff that's in there, all the stuff that's in the Walmart was not made here. It was made thousands of miles away. Human beings take stuff that we make and we move it, and we move it in large quantities. Okay, that's important that we do that. We trade things, all right, and that's how one of the ways. It's one of the bases for actually having a civilization is the ability to take things that one people make and then trade it with other people, okay, and vice versa. So that's very important. And as time went on, as we became a species and we started making towns and then cities and then eventually nations, and we started to move even more stuff and come up with better and better ways of doing that. First it was animal trains, all right, and then it was then we started to do it on boats, and the boats got bigger, and eventually we made these very complex sailing ships, and so that could actually even go slowly, but could actually go all around the entire planet. And then eventually 2 centuries ago we started making machines to take over for the wind power, and we started making trains to go over land and putting motors on boats so that they could go wherever they wanted in the world without having to depend on the wind. And obviously in the modern age we still use trains, although they're more updated, but we also use aircraft in large quantities to move things from one place to another. Okay, and also gasoline or diesel powered vehicles called trucks to move large quantities of stuff. All right, so that's why it's important. Okay, now the first thing I want to say is this, that motion is not, well, let me ask you this. Let's start off with this one. Here's my Rubik's Cube. Why am I using it? Because it's just right here. And if you take the Rubik's Cube and I toss it up and down like that, so it went up and then it went down relative to me. Up and down. and I would ask you, how far did the Rubik's Cube move? And you probably said like maybe about 2 feet. It went about a foot up and then dropped another foot. So when you put those together, that's like 2 feet. And you'd be right in one sense. But in another sense, and I tend to do this in class, but obviously we're not in class, I would say then, all right, what are you standing on? Well, I'm standing on the floor. Well, what's the floor on? Well, it's in the building. What's the building on? Well, it's on the earth. Is the earth moving? Yes, it is. The earth is moving actually very fast. In fact, the earth is moving 20 miles every second as it goes around the sun. So it's going in a big circle, and in that circle it moves sideways 20 miles every second. So when I say 1/1000, you just moved 20 miles. All right, you didn't feel it. And we'll go into that later because you didn't accelerate, and we'll talk about that a little bit more. You didn't feel it because the earth is also a completely smooth ride. It's not like it's on a road or has a suspension. It's out in space. But you move 20 miles every second that you're alive. You were born moving 20 miles a second. So in another sense, as this goes up, leaves my hand and goes up, it's also going to the side 20 miles. I'm going with it, so I don't see that. And as it comes down, it goes down, as it comes down, it's also going sideways as it goes down another 20 miles. So 1/1000 to 1,000, it's in the air 2 seconds. In 2 seconds, it went 40 miles to the side. So in one way of looking at it, okay, the Rubik's Cube went up, and then it just went back down. In another way of looking at it, it went up, but it also went sideways in a big, huge arc. So it went up a foot and down a foot, but it went 40 full miles to the side as it went up and down. So the question then arises is, what is right? Okay, well here's where you get an education, all right? And the answer is they both are right. And here's something that you need to know, because coming from the middle school and the elementary schools, all right, human beings are often taught, well, there's only one right answer. No, it depends, all right? And what does it depend on? It depends on something called a frame of reference. And make sure you have that in your notes, because I'm going to ask you questions about that, do Google Forms on that, things like that. It's a very important concept. Motion depends on a frame of reference. In fact, I want you to make sure you have this down. There is no motion without a frame of reference. There is no motion without a frame of reference. And what is a frame of reference? A frame of reference, very simply, it's not a very scientific definition, but what a frame of reference is very simply something used to determine if you're moving. Something used to determine if you, and I'm going to contract it, you're moving. Okay? All right, and there you go. So, when I look at the Rubik's Cube, and here I have it, when I look at the Rubik's Cube, in one frame of reference, in the frame of reference of the room, that's what I'm using to determine if it's moving or not. It just goes up and then down. In another frame of reference, the outside the Earth, it goes 40 miles to the side in a ballistic arc, which is true. Both, depending on what your frame of reference is, okay? But you have to pick a frame of reference, okay? So that's what's going on there, all right? So, all right, I'm going to give you guys a series of questions. Well, actually, the other thing I want to say is, where does this come from? This actually comes from Einstein. Einstein wrote about a little over 100 years ago a theory called relativity, okay? And the word relativity means in relation to, okay? So relative. And remember what I keep telling you guys, to learn the language. Learn as many words as you can, okay? The more intelligently you can speak, the better you can speak, the more people will take you seriously. And I always keep telling you guys that. Remember that. Okay? That's not science. That's just being a functional adult in life, which eventually you guys are going to be. Okay? But the word relative means in relation to. Okay? So relative to a frame of reference, in relation to a frame of reference. So in relation to the room, the Rubik's Cube only goes up and down. In relation to the Earth, it goes in this ballistic arc that's 40 miles wide. That's what a frame of reference is. And again, you need to have a frame of reference, because imagine yourself out in space, okay? Imagine yourself out in space, right? And I know I just showed you a Rubik's Cube, but I'll get back to why I did that. But if you're just like out in space, away from the planets and the stars, and just this dark void area, how would you know if you're moving? And you're probably saying like, well, I can feel it. No, you can't. You can't feel moving at a constant velocity. You can't. Do you feel like you're moving when you're on the Earth? No, you don't, even though you're moving very fast. Okay? What you feel is when you speed up, slow down, or turn, and we're going to get into that later. It's called an acceleration. That's what you feel. Okay? You feel a change in motion. When you're driving on the road, you feel the bumps in the road. Why? Because your smooth ride is getting changed by the bump. And you feel that. That's how you know. But if it was a completely smooth ride, you wouldn't really know if you're moving or not. Just like you don't know, like most people don't feel like they're, that's one of the reasons why people thought that the Earth stayed still and the sun went around it for thousands of years, because they don't feel it moving. Okay? So make sure you know that, and make sure you understand that. Okay? All right. So anyway, imagine yourself out in space, and you're just kind of floating there. And if you were out in space, the question is, how would you know if you're moving? And the answer is, if you can't see anything but blackness, and you're not speeding up or slowing down, you wouldn't. You wouldn't know if you're moving. You would have to have another object out there. So imagine now the Rubik's Cube is out in front of you. If the Rubik's Cube is just floating in front of you, you would say, oh, I'm not moving. Why? Because it's not, this thing isn't getting any closer or farther away from me. But if it was moving towards you, you could say one of two things, or three things. You could say, oh, there's motion here. I can see it getting closer. So, one, it's either getting closer to me and I'm standing still, it's moving and I'm standing still. Or two, it's standing still and I'm moving closer to it. Or three, we're both getting closer to each other. I'm moving and it's moving at the same time. Those are three valid assumptions that you can make. But you need to have another object out there to determine if you're moving or if anything is moving at all. Okay? And the other object is called a frame of reference. Okay? So make sure you have that. All right. Now, I'm going to ask you guys a series of questions. All right? And I'm posting them. And all I want you to do with these things is to take a look at them, read the scenario. Okay? Like in the first scenario, I think it's the first scenario, you have a bus. Okay? And I'll describe it to you. All right, and make sure you're watching these videos, because I'm going to know if you don't, because then you're going to say like, oh, I don't get it. All right, because I'm describing it to you like right now, especially the first one. And let's say you're in a bus, and here's you, and you're standing on the bus, which you shouldn't be. You should always sit down when the bus is in motion. Remember, safety first in a zombie apocalypse. All right, and the bus starts to move. Okay, and then here's some dude, and he's standing there. Grandma Golis would say like so. And he's standing outside the bus. And this guy puts a softball down on the bottom of the bus, on the floor. Why? Who knows? Whatever, but just go with it. And let's say that you can see inside the bus. Like it's got like the whole side of it is just like one big window. Just go with it. It's called a thought experiment. Okay, now the bus takes off. So initially the bus is at rest, and now the bus speeds up. So the first question is, the question is, what does this guy see the ball do? If you're in the bus and you put the ball on the floor of the bus when it's not moving, then the bus takes off and moves forward, what do you see the ball do? And then I want to take a look at this. And this guy right here, if he's standing outside the bus, what does he see the ball do? Does he see the ball? Well, I don't want to say. But what does he see the ball do? And I want you to describe that. All right? Because I want you to think about this stuff. It's important that you guys have opportunities to think. Okay? So, in this guy's frame of reference, what does he see the ball do? In this guy's frame of reference, what does he see the ball do? Okay? Now, I believe it's like question number 4. All right? I just sent you like the Google Doc, and the Google Doc doesn't have my handwritten drawing in, so I'm putting the drawing right here. Okay? Which, again, is going to be one of the ways whether I know you're actually watching my video, which is now 15 minutes long, because I'm putting the diagram right here. Clever. Clever of me. All right, and the diagram looks like this, but here's the question. So you have one star over here and another star over here. And then you have 3 points. So here's point A, and then here's point B, and then here's point C. Okay? And these stars are 1 light year apart. And then point A is 1 light year from this, we'll call this star number 1 and this star number 2. 1 light year from star number 1. And point C is 1 light year from star number 2 on that side. So let's say this happens. So let's say that you're standing at point B, okay? Kind of centered in between the 2 stars like that. And let's say that both of these stars explode at exactly the same time. That you, at point B, you see both of these stars blow up at exactly the same time. The question, and so the question I have for you, and this is what the question number 4 is, if you're at point A, do you see both of these stars blow up at the same time? And if you don't, what order do you see them blow up in? And what time difference is there? Okay, so do you see one blow up sooner than the other? And if you do, when does the second one blow up relative to you? If you're at point C, all right, do you see both of these stars blow up at exactly the same time? And if you don't, what order do you see them blow up in? And what's the time difference in between them, in between their explosions? Got what I'm saying? Okay, all right. So I already made this video like 17 minutes long. All right, so make sure you pay attention to it. Make sure you do the assignment. Write down your answers on a Google Doc, okay? So I can read them and sort of take a look at them, okay? So that's what I want you to do, and that's your assignment. See me during my office hours, all right? Okay, so goal is out, and have a fun apocalypse.